Okay, and I'm starting the recording like because if you have like some issue of internet and all, at that time you can use the recording, but it not like that you don't focus in this live session and you just see the recording, right? Otherwise I will give you the recorded videos, right? If you want to focus on that, then I will do that. Okay, so focus on this live session, what I am teaching. Okay, so we have discussed this thing, right? So address means in bits when it is a logical address space or a virtual address space, then it's in bytes, right? Physical address, physical memory or main memory size, that is PAS, physical memory size, right? Your main memory size, that is in bytes. So this 23 bits of physical address, it indicates that the bytes, total bytes that I have in main memory, to give address to each byte, I require 23 bits. If I have 23 bits, then I can give unique address to each byte, right? Then we have seen this logical address, how it divides your physical address. So basically what we'll do, we will divide your logical address space, means that process size, into pages, and that page we will put into main memory, right? So the same size we have in main memory, so same page you can just take and put into main memory, right? And how this equation comes, that we have already discussed, but my suggestion is not to focus directly on this equation, but understand what this term is. Once you understand those terms, you can easily write this thing. Easily लिख सकते हो, right? Pages in logical address space, capital N, M. No need to means just remember this thing. You can easily write this thing once you know. Right? And once you know the terms, that will be easy for you as well if there is a twist in the example. Okay. So then we have identified the page table size as well, and that is 256 KB. And I have given this example to you. Now, explain me the solution of each of this question. If you have solved this, you need to tell me first answer and why that answer.
So number of pages in LAS is 2 power 20.
Number of pages in LAS is, okay, let me write this thing. Logical address, then we have physical memory and page size. Physical memory and page size we have, so logical address is 32 bits. 32 bits, this is 4 KB, and physical memory is 64 MB. This thing I have, right? And the answer that I need to find out is this thing. How many pages in LS, PS, this thing. Okay, capital N, right? Number of pages. Then in physical address. How many pages in physical address space? That is M. Then number of entries in page table. Number of entries in page table. Right. So this is easy task, I think, because it depends on this capital N. So it is the same thing. Then offset D and your page table size, right? And let's write small p, small f to indicate bits required to address pages and bits required to address frames. And here we are considering page and frame size are same. Okay. Yes. Who was talking? I think Vivek.
Yes, sir, it's 2 power 20.
The answer is 2 power 20. Now Vivek will tell how.
So number of pages in LS is equal to like size of LS divided by page size. So size is 32 bits.
Yes,
So
page size. And what
so
is
size is
LS? 2 power 32. And page size is 4 KB.
4 KB, so 2 power 12.
2 power 12. Byte, byte. Yes, so byte cancel. 2 raised to 32 minus 12. That is 2 power 20. 2 power 20 pages are there. So the process, if you consider that LS size of 2 raised to 32 byte, that is divided in 2 raised to 20 pages. 2 raised to 20 pages, right? Okay. Now someone else for capital M.
So 2 power
Sir, 2
14.
power 14.
2 power 14.
2 power 14. Who was there? 2 power 14.
Yes, sir.
Jill.
PAS by PS.
Okay, so what is that M indicates?
Physical memory.
Capital M.
Physical address space.
Number of
This
pages.
Number of
Physical.
pages in PS.
number of,
Pages in page physical address space.
yes, it's number of pages in physical address space. So to find out that, you know, that something I have, I need to divide by page size. And what will be here?
PAS, physical address space.
So
2 raised to
physical
26.
address space. If you divide by page size, you will get this. What is PAS?
2 raised to 26.
It's this thing only, 64 MB, right? So M is 2 power 20 and 64 is 2 to the power 6. So this is 2 raised to 26 byte upon page size 2 raised to 12 byte. So 2 raised to 26 minus 12, that is 2 raised to 14. Okay, now offset. First you need to tell me what is this.
So page offset.
Yes, but what is exactly?
Sir, gives exact bytes in pages.
Yes, yes,
The unique identifier.
yes. So it will execute tell, once you have a page, it will execute tell in that page where your byte is. Where your byte is, it will tell that thing, right? Okay. So how we will find out this thing? I'm not asking answer. How we will find out this thing? अभी जो मीन्स आपने बोला अंडरस्टैंडिंग इज परफेक्ट, राइट, कि पेज में वो बाइट कौन सा है वो मुझे जानना है, सो दैट इज ऑफसेट। तो वो मिलेगा कैसे?
Sir, number of bits required to to index page size bytes is D.
पेज साइज, yes Ved, you can try again.
Yes. Means I have to tell the equation or
No, just in layman term you need to tell, not equation. So D is number of bits, that is correct.
So the page size is 4 KB. So the number of bits required to allocate that 4 KB. That is the offset. So it
yes.
will be log of 4 KB.
Yes. So in one page, the bytes that I have, in one page, the bytes that I have to address to that byte, to give address to each bytes, how many bits are required? The D indicates that thing. So my page size, it depends on what? Your page size. So how many bytes you have in your page? 4K. 4K bytes you have in your page. So 4K means 2 raised to 12. So 2 raised to 12 bytes you have in one page. So once you got the page, now you will differentiate in bytes. Now to differentiate this byte, how many bits are required? That is 12 bits, right? So D is 12 bits. So in terms of equation, how will you write?
Log of PS base 2.
Log of PS base 2. Right? Okay. Now before finding this page table size, let's write this P, small p. The unit for both this thing will be bits. It is a part of logical address and your physical address. D. This is your P. This is your F. P.
It is the bits required to map the pages in the logical address. So we will get by log of 2 power 20.
Okay, again you can try.
The bits required to map the pages in the logical address, LAS.
Again.
Sir, number of bits equal to address number of pages in logical address.
Yes. So it is bits bits required to address each page in logical address space. Right? Small f.
Number of frames in physical address space.
Yes, bits required to address each frame into physical address space. Right? So it depends on this. So 2 raised to 20 pages I have in logical address space. To address these pages, how many bits are required? That is 20 bits. In terms of equation, what you can write?
Log
Log
of
n
n
to the
base 2.
Yes, log n base 2. For F, it is a 14 bits. How you can write log m base 2. Okay. So basically what is happening when CPU generate your logical address, that 32 bits, this is divided in some portion of P and D. Now your P is 20 bits and D is 12 bits. So just see whole bits, 32 bits, whatever the value in that is divided in two portion, 20, 12. 20 and 12. Same way your physical address that is divided in two part, D is fixed, that is 12. Your F is 14 bits. So this is 14 bits PA, right? What is that PA? Okay, still we have not find out the PA, so you can write this PA, number of bits in physical address. How many? Not here, this one, PA. That is physical memory.
26.
Yes. So PA is 26 bits. What is physical address? If your physical memory is divided in bytes, that we are considering, your physical memory is byte addressable. So to give address to each byte, how many bits are required? That is 26 bits. That is 26 bits. Right? So this is 26 bits, and you can see 14 plus 12, that is 26 bits. Right? So means your address is divided in portion, and then by some method you convert this logical address into physical address, means this 32 bits into 26 bits. Okay. Now one thing is left, page table size. So page table size, let's write here, page table size is equal to how, means on what the page table size depends.
Pages present in LAS.
Yes, pages, number of pages in LAS, that is capital N, and
The frames in each page.
and
Multiply by 14.
and the entry, right, means at each index what is the entry, it depends on that thing. So entry, if I indicate with small e, I am indicating with small e, right? So now capital N, what is capital N? 2 raised to 20. Now e, so see this is e, means one entry size, one entry size. This is E, one entry size. And for simplicity, we will convert E to nearest byte, to nearest highest byte. Right? So entry will give you the frame number or the page number of physical address, that is F. So 14 bits are required. Right? Below that I cannot take. So the nearest higher value is 16 bits, you can consider 16 bits, and that is 2 byte, that is 2 byte, right? And E is 2 byte. Without this, if you want to write directly, then this will be 2 raised to 20 into 14 bits. This will be the thing, right? But this not looks good, right? And for comparison also it's difficult. So we converting into bytes. So this 14 bits we are converting into bytes. આટલું જ convert કરીએ છીએ. And we are converting to the upper one, that is 2 byte, right? You cannot take 1 byte, otherwise the information will be lost. Okay, so 2 bytes, so this will be 2 raised to 21 byte. In terms of mega, if I want to write, then this is 2 MB. This is 2 MB, your page table size. Now any doubt in this?
No, sir.
Jainil, roll number 6.
No, sir.
Yogansi, 14.
No, sir.
Yash, 27.
No, sir.
Bhavya, 33.
Yes, sir.
Bhavya 33. Okay, Nikhil 48.
No, sir.
Nirman 68.
No, sir.
Darshan 95.
No, sir.
Mohit 114.
No, sir.
138. Vraj.
No, sir.
174.
No, sir. No doubt.
Okay, 185.
No, sir.
Okay, that's good. So hope you understand this concept, and now you can solve the example of this on paging, right? Now let's move to some performance metrics for this, and you might be aware about the effective memory access time. This thing we have used in CO as well. So same thing, we will use that here as well, right? Okay, so now tell me, when you will search your, or when there is a conversion, right, logical address to physical address, how many memory access will be there? लॉजिकल एड्रेस फिजिकल एड्रेस में कन्वर्ट हो रहा है. हाउ मेनी मेमोरी एड्रेस मेन मेमोरी एक्सेस विल बी देयर? कितनी बार मेन मेमोरी एक्सेस होगी?
That will be equal to the number of pages the process has.
वाई पेजेस? कोई एक लॉजिकल एड्रेस जनरेट हुआ, उसका मुझे फिजिकल एड्रेस चाहिए.
That is because if the whole page is inside the main memory, then we don't need to fetch it. Then the whole cluster of the related memory locations will be present. So if that whole cluster is present in the main memory, we don't need to fetch all the pages again and again.
Okay, but there is a memory access, or you can say, I'm not saying the transfer or that thing, just you need to go to main memory.
So it will be every time the CPU needs something.
Okay, Ayushman. Now let's think in this way, that you have some logical address that is generated by CPU. Now you are memory management unit, and you are now converting that logical address into physical address, right? So how many time you will access main memory? Okay, so for that, what you should do now, just think the logical address portion, right? What first step you will do? Just tell me step by step.
So we will first generate the logical address and then
Yes,
go
that
to
is
the page.
generated. That is generated by CPU logical address.
Yes. Then we will look for the physical address across the page table.
Okay, so
So we will
you
convert the
will,
logical address to physical address.
yes, but if I fine grain this thing, then your logical address means has a two part, that is page number and offset. Yes.
Yes, sir.
Now page number, what you will do, where you will search your page number?
In the page table.
You will search in the page table. Where will be your page table?
It will be in the main memory.
So page table is in your main memory and it's in kernel space, right? Or operating system space.
Yes.
So that is a memory access.
Yes, sir.
So that is a one memory access, right? Now I have a table using page number. I will look into the page table, and from that entry, what I will get? I will get a frame number. Now I have a frame number. I have an offset. I will combine that, and now actual physical address I have means the byte that I am looking for, that byte I have a physical address. Now to get that byte, again I will go to memory.
Yes, sir.
Right? So how many memory access are there?
Twice the number of memory locations that the CPU requires.
Twice the memory.
Twice the memory locations that a process holds.
No, why memory location means?
Inside the number of accesses the process needs to make, it will be just double that.
Yes, but right now, our focus is only one logical address. Right?
So then 2.
Yes. So it's 2, right? And if I indicate the memory access time as M, then it is 2M. So every time, whenever you generate logical address, the 2M time that is used for this memory access, right? And suppose some frequent pages are accessed, right? That is also happening, right? From whole program, some portion are accessed frequently or some are used frequently, or it may happen that it depends on time. Means right now if I accessing something, the chances of that access in near future is high, right? So that is a frequent access. So what I can do is I can have a TLB, that is translation look aside buffer, right? So what I will do, I will keep these entries, right, which is accessing uh, more frequently, that I will keep in translation look aside buffer. So this is your translation look aside buffer. What I will keep here, that I will keep logical address, and for that what is the physical address, right? And the TLB access time, if I indicate with C, then this TLB access time is very less than M, is very less than M, right? So if when your CPU generate logical address, what it do first, it will check into TLB. It first check into TLB, And if this logical address found in this TLB, right? And what is the time to find this? C. Once you have this logical address, then the respective physical address you have, and from that address you can get your byte. This is your byte. So this is memory access. So in this case, when your logical address found in TLB, the access time is C plus M. Assume that you search in this but data not found. Then
C
what you
plus
will?
2M.
Yes. So in this case, what you will do? The method that we are doing. So the CPU will search in the page table, and this page table is in main memory, right? So this is M, and then from page table I have frame number and your offset. So using that physical address, right, F plus D, you will get F, and using that you will find which byte. So now in this case it is C plus 2M. In this path it will be C plus 2M, right? 2M for this, and as first it search in this, so that time also we need to count. But if it founds in TLB, so that is C plus M, right? So when your logical address found in TLB, that is called hit. If it is not found, then miss. So what should be the ideal scenario? What you should increase? You should increase the hit ratio. More the hit ratio, it will take less time. More the miss ratio, it will degrade your performance. Right? Which you can achieve without TLB as well. Right? So if hit ratio I indicate with X, then my effective memory access time, how can I write? Hit ratio, you know, I think, right?
There's a hit ratio into C plus M, and then miss ratio into
Yes, hit ratio
C plus
into
2M.
C
C
plus
plus
M
M
plus.
plus miss ratio.
Okay, how can I write miss ratio?
So that will be 1 T minus X.
That will be
1 minus X. So that will give
yes,
us
1 minus X, right? And
multiplied by C plus 2M.
C plus 2M, correct. This will be your effective memory access time, right? This will be your effective memory time. So hit ratio is from total reference. Suppose 100 times if you generate logical address, how many times it founds data in your TLB. Suppose it found 70%, 70 out of 100 times if you generate logical address, 70 times it founds the logical address in TLB, then that will be 17 upon 100, right? 0.7. And what is miss? Reverse.
0.3.
Yes. So out of 100 reference, how many times the data logical address is not in TLB? That is 30. So that is 0.3. So if you sound this, that will be 1. So that's why I'm writing like this, X and 1 minus X. And this is correct. Effective memory access time. Okay. Any doubt in this?
No, sir.
Okay, so the main thing is the effectiveness of this approach. It depends on what TLB hit. It depends on this TLB hit. More hit means you will take this time, right? If it increase this thing, then it will give you a worst performance, right? Okay, now solve this simple example. Your memory access time is 100 nanosecond. Your TLB access is 20 nanosecond and your hit X is 90%. What will be the effective memory access time? Tell me.
One 30 nanosecond.
130.
30.
Okay, everyone getting that 130?
Yes, sir.
130 nanosecond, right? So this is the effective memory access time. So if I remove the TLB and then if I need to find out effective memory access time, that is 200 nanosecond, right? Without TLB, because it's a 2M. And now just keep X is equal to 10%, remaining M and C as it is. What will be the effective memory access time?
Two one zero.
210 nanosecond. Right, so just see the impact. The good TLB hit will reduce your effective memory access time. This reduce in TLB hit will give you 210 nanosecond. Right? Any doubt in this?
No, sir.
Okay. Now let's take the intuition of next thing. Okay, so we store the page table in main memory, correct?
Yes, sir.
Right. So suppose your entry size is very high, and generally it happens, right? Because you have a process of larger size. So in that case, the number of entry increases. The increase in number of entry indicates what? It leads to it will increase the page table size or will reduce the page table size.
It will increase the page table size.
Yes, so it will increase the page table size, right? It will increase your page table size, and your page table we are putting into memory or your OS, right? Sometime I use word V, right? So pardon me for that. So it's a OS. OS will put that into your main memory, means that space are occupied of main memory for page table, and as you increase that page number of pages, so number of entry will be increased, right? And that will be stored in page table, right? So it will lead to a memory uses. It will relate to memory uses, right? It should, and just assume 100 processes are running, right? And for that you require page table in that, and it's a simultaneous, right? So one by one it's running. If it is not running, then and then you can put into another location. But if it's a running ready state, then you cannot put into a hard disk or something. It must be in main memory. So just assume for that how many spaces are required, right? So what approach we should use, how we should deal with this thing? So there are number of students, right? And I am maintaining one file. I am maintaining one file, and that file contains the ID number of each student, right? ID number of each student. Now, if I have more students, then the file size of that file will increase. File size of that file increase.
Yes,
And that file I am putting in main memory, and I want to reduce that thing. ताकि file अंदर मुको जो main memory में, right? It's not a good thing that whole. It's not required, I think, right? Because every time you don't require the data of all the students. So,
sir, it is the concept of paging.
yes, what, Ayushman?
Sir, the concept of paging, like we load only the required pages in the main memory.
Okay, right now this is paging only, right? What we are considering is a concept of paging, and each student is a page. Each student is a page, and Charuset whole is one process. Charuset whole is one process. So in that, Charuset whole is one process. So when I want to execute Charuset, at least the page table of Charuset I require. It may possible the page related or the student I don't require at a time, but the page table of Charuset I require. Charuset માંથી મને student no data find કરવાનો કે, right? And I am maintaining only one entry, whole list, Excel sheet of all Charuset student. What I need to do? I need to find out that file and need to search that student.
Yes, sir.
But that whole file I need to use. So
yes, sir.
what
Since it is
can
one
be
file, you need to
yes.
like linearly go through everything.
So what can be the effective thing?
Sir, during the first search, we can get like a portion that is above and below the entry that we fetched.
What you can do above?
Sir, like if we have 5 pages, like if we have 100 pages and we search for like let's say the 50th page, then we load the 2 pages above the current page and 2 pages below the current page inside a faster memory such as cache.
Okay, but will it reduce the page table size? Means મારે file
No,
load
sir.
ના કરવી પડે એવું થશે?
No, sir, but like it will reduce the access time.
Yes, maybe access time will be reduced, right? But right now our focus is the page, the file that I'm putting in main memory. That is my problem. The file that I'm putting is my problem. So one thing I can do is, rather than individual student, what can I do? I make a page, I can increase the page size. What can I do? I can increase the page size. There are disadvantages of it, or I can reduce the page size. I'm talking about page size. What the impact of increasing page size to page table? If I am increasing page size, तो उसकी क्या impact पड़ेगी?
So the page table will reduce in size.
Sir, internal fragmentation.
Yes.
हो सकता
Yes, the impact is internal fragmentation, and one advantage is it will reduce the page table size. Correct?
Yes, sir.
Okay. So just keep this thing in mind, right? And the next lecture we will start on this base, right? On this base we will start the next lecture, right? Okay, so thank you for joining, and let me end the meeting here. And tomorrow the OS lecture what you have of Padma ma'am, that will be a same, right? जो last time हुआ था वैसे ही होगा. First one will be combined for both the division, और second में वो डाका होगा lecture. और on Monday जो मैंने भेजा है वैसे execute करेंगे. Means for both the division I will take a combined lecture Monday and Thursday, दोनों time. Okay.